Hello everyone, today I will be presenting our paper, PAAS, a preference-aware deep reinforcement learning approach for 360 video streaming. My name is Wu Changlei, and the other authors of this paper are Professor Wang Zhi and Professor Sun Yifeng from Tsinghua University, China. The content of my presentation is as follows. So first, I will talk about the background of our paper. In this paper, we focus on the optimization of 360 video streaming. As we all know, 360 video is believed to be the killer application on virtual reality devices. It is normally watched by users with head-mounted devices, and it can provide users with immersive viewing experience. So the 360 video online streaming has two main features. On the one hand, it consumes a lot of network resource. High-resolution 8K or 16K 360 video streaming can cost hundreds of megabits of bandwidth. However, on the other hand, the bandwidth utilization is very low. This is because in every moment, only the viewport video content within user's viewport is actually watched. These two features makes the high-resolution 360 video streaming to significantly challenge today's video delivery system. To cope with these problems, the bandwidth-efficient 360 video streaming methods have been proposed. This method is also known as the Viewport adaptive streaming methods. In these methods, they will first predict the user's future viewport and only download the related content. The most popular Viewport adaptive streaming method is the tile-based method. This method divides a 360 video into multiple regions or tiles and only download the tiles that are related to the predicted viewport. For example, the predicted viewport. The disadvantage of this method is that they can cause extra encoding overhead, but compared to other methods, it is still the most practical one, and thus it is used in the baseline methods and this paper. Furthermore, the recent 360 video streaming methods often adopt the DLL-based adaptive bitrate algorithm to allocate bitrate or bandwidth for tiles. The reason is that the DLL-based methods are more adapted to the vast state of network conditions. So the SourceUp-based method often adopts the fixed sequential tile download order, similar to the conventional video streaming. So in the conventional video streaming, the video content are divided into chunks and downloaded sequentially. So for example, after downloading the chunk number 5, we will be downloading the chunk number 6. However, this sequential download process is problematic for the 360 video streaming. In tile-based 360 video streaming, each downloaded video chunk is related to a viewport prediction. So after a chunk download, for example, after downloading chunk number 5, if we update the viewport prediction for the following chunks, we may find out that the new viewport prediction is different from the previous prediction. For example, the chunk number 4 and number 5. This means that the chunk number 4 and number 5 are not downloaded correctly. So if we follow the sequential download process, we will then be downloading the chunk number 6 instead of correcting these mistakes. So what's the impact of this sequential download? We compare two types of API algorithms. The first is the prefetch-based 360 streaming methods. These methods continuously download the video chunks until the buffer is full, and the buffer size is larger than 1. So the advantage of this method is that they can maintain a large buffer and are more robust to the network fluctuation. But the disadvantage is that these methods download the video chunks as many as possible. So their prediction time window is much larger. They often have a very large prediction time window. So, and as we know, the viewport prediction accuracy is low, goes low when the prediction time window goes higher. So in our experiment, we found out that the DLL 360 methods often download the video chunks almost 4 seconds later in average, and it decreases the prediction accuracy by 24.9%. The other, to avoid such larger prediction time window, another type of ABI algorithm is the fetch-based methods. The fetch-based methods only download the video chunks, only download at most one video chunks, so the buffer size is 1. The advantage is that they can maintain a shorter prediction time window, so the prediction accuracy is higher. But the disadvantage is that they can only maintain a small buffer, so they are more likely to suffer from the network fluctuation. So in our experiment, we found out that the representative SRL 360 methods, they wasted more than 20% of the bandwidth, and doesn't use this bandwidth to build up the buffer. So in summary, the sequential download process may work for the conventional video streaming, but it can cause a trade-off between the bandwidth utilization and the prediction accuracy for tile-based 360 video streaming. So this problem is also known as the prefetch aggressiveness problem. In previous methods, previous work, there are also previous work that try to balance this trade-off. For example, in the ICAS 19 paper, the authors try to encourage the player to maintain a small buffer while not causing the under the premises of not causing rebuffering event. So can we simply avoid such trade-off instead of balancing this trade-off? So in the baseline methods, the trade-off is caused by the DI agent that can only decide the bitrate. So if we can support the dynamic tile download order, if we can support the dynamic tile download, for example, retransmitting the tiles that are downloaded that are not downloaded correctly, then we can overcome this trade-off. A simple solution is that we can let the agent to decide both the bitrate and the tile download order. But the disadvantage is that it will increase the decision space by hundreds of times, which makes it difficult to train and deploy. So in this paper, our motivation is that can we achieve adaptive tile download while not incurring large overhead? The second part is the methods. Our method is a preference-aware dual-queue 360 video streaming method. Compared to the SourceUp methods, which only have a single download queue and the fixed sequential download order, our method is a dual-queue download framework. The first queue is a fetch queue, which downloads the next chunk that will be played immediately. This queue is designed to achieve high prediction accuracy. And the second queue is a prefetch queue. This queue only downloads the non-urgent chunks, and it is designed to achieve high bandwidth utilization. We also achieve the adaptive tile download by updating these two queues asynchronously based on the most recent Viewport Prediction. Based on the dual queue structure, the DI agent can achieve the adaptive downloading with very simple decisions. For example, they only have to decide which queue to select and which bitrate to download. So compared to the SourceUp methods, the decision space of our method is only 2 times larger. We also design a dual DQN-based network to make the DIL agents the DIL decisions. The DQN network takes input of the Viewport Prediction, network condition, and user preference as inputs, and it outputs the estimated value for each action. We also design a mask-based action sample strategy to disable the illegal actions during the training. Furthermore, we also design a preference-aware DIL agent training strategy. In 360 video streaming, the QoE or the reward is defined as a weighted summarization of many streaming metrics, for example, the bitrate, rebuffering, or the smoothness. The importance or the weights of these metrics depends on the user's preference. For example, some users may prefer high bitrate, others may prefer low rebuffering. So the SourceUp methods have to train one model for each preference, which will cost a lot of training resource. So to deal with this problem, we propose a one model fits all solution. Our solution is composed of two techniques. The first is the aforementioned preference-aware decoy model. The second is a preference-aware training. So to put it simply, the preference-aware training strategy will train each state action transition with not only the original preference, but also a randomly sampled preference, such that our model can scale to the unseen preference and then understand the connection between the action and the user preference. So the details can be found in our paper. The final part, the third part is the experiments. So we first conduct the experiments on the real-world data set between our method and the baseline methods. We found out that the quick update algorithm can significantly can affect the final performance, especially the rebuffer. Furthermore, our method is able to achieve 99.7% bandwidth utilization. On the HSDPA weak network dataset, our method can achieve 13.6 QoE boost compared to the best SIL 360 baseline. We also compare our method with baseline methods on the different preferences. On the trained preference, our method can achieve a 13.8% QoE boost, and on the unseen preference, our method can achieve a 19.9 QoE boost. And the details of these experiments can also be found in the paper. So the final part is the conclusion. In summary, we first show that the SOTA method doesn't provide the best QoE. These methods don't allow the retransmission or dynamic tile download, so they suffer from the trade-off between the prediction accuracy and the bandwidth utilization. We also propose paths to counter this problem. Our method is composed of a dual-query dynamic tile download framework and a preference-aware DIL model and the agent training workflow. We also conduct extensive experiments to demonstrate the performance of our methods. And we also trained our method and the baseline method with the tile level 360 video streaming simulation environment, and show that our methods can achieve 13.8 and 19.9% QoE boost on trained and unseen preference. So this is all, and thank you for your attention.